Today I want to move to the maybe more interesting, more interesting to most people question of counting Higgs bundles. Counting stable Higgs bundles. So I will be interested in the case where stable is the same as semi-stable. Okay, so let us fix R and D such that the GCD of R and D is equal to 1. So people are usually interested in the moduli space of semi-stable Higgs bundles, and in this case, semi-stable is therefore smooth because it coincides with the stable Higgs bundles. And so some corollaries of this is that Higgs stable RD is equal to Higgs semi-stable RD. So stable is the same as semi-stable. And also for indecomposables, indecomposable implies absolutely indecomposable. Okay, so this is the most interesting situation. And the aim is, well, since we saw how to compute indecomposables, or absolutely indecomposable, it's the same thing for these dimension vectors, the aim is to show that the number of stable Higgs bundles of rank R and degree D, so the number of FQ points, is equal to up to some power of Q, which is 1 plus G minus 1 R squared, times the number of indecomposable vector bundles on our curve X. Okay. So morally, you can think that this parameterizes, this counts the number of points of an algebraic variety, which is twice the dimension of the moduli space of stable bundles. And the number, and a generic stable bundle is probably going to be indecomposable. So this roughly has the size of the number of stable vector bundles. And so this says that up to some power of Q, which agrees with the dimensions, these two should be the same. So the first idea, so this looks rather strange, but the first idea, which fails, is to consider the projection. There's an obvious projection from Higgs bundles, so you can restrict to stable Higgs bundles, to vector bundles, and hope that by some miracle this would be a fibration over the constructible subset of indecomposable vector bundles. Right? Lands into, let me write, indecomposable RD, which is inside Bun RD. So this is just wrong. You can construct stable bundles whose underlying bundle is not at all indecomposable. So this map is not going to help you. So I should mention. So I should mention that this problem was solved. Exactly this problem was solved in the context of Quivers a few years ago. So in the context of Quivers, you can ask exactly the same question. There is an analog of this stable Higgs bundles. This is not too far from Nakajima-Quiver varieties, except that we have no framing in this case. But this exact equality, the analog for Quivers, was proved by Bill Crowley-Bovey and Van den Berg. And in the same paper, there is also an appendix written by Hiraku Nakajima. And so this gives us really hope that this theorem will hold. And actually, this also gives us the method. So we have to adapt the method to this curve setting, but really most of the ideas, the fundamental ideas, are already in this paper. This is a really, really beautiful paper. So what is the key idea? The key idea has already appeared in some form in Victor's talk. Namely, we're going to construct some deformation. So we have this moduli space of stable Higgs bundles, and we're going to insert it into a certain family. We can take a one-dimensional family. And this family is going to be, all the fibers are going to have the same dimension. Actually, all the fibers, in their case, and I haven't checked it in my case, but I'm quite confident it holds, all the fibers have the same cohomology. And so there's some nice identifications of cohomology, number of points. So let me say this is FQ points are the same for all fibers. And we're going to construct a map. We're going to extend the map from vector bundles, two vector bundles, from this moduli space of stable Higgs bundles to this Y. So here we have when R D, and we extend this map. And now if we restrict this map to the complement of 0, to the deformation, then it lands into indecomposable, and it's a fibration. So this is the key idea. So let me say for t different from 0, let's say you restrict the projection P to yt. So now it goes from yt to bun rd. This is, well, you have to be a little bit careful, but let's say this looks like a affine fibration. Over the constructible subset of indecomposables. And this does the trick, of course, right? So you are able to deform this moduli space of stable Higgs bundles, and you deform the map to Bunn so that everything works out very nicely, and this naive idea is actually true. So how do you construct this deformation? So I would be tempted to say that modern, so let's say the modern 21st century professional mathematician way to construct Y would involve, I'm sure, the words derived, cotangent, stack. But unfortunately, I'm stuck in the dark ages, so my method is constructed explicitly using charts, which is really something ugly, using local presentation, let's say. Local presentation of Higgs bundles, of the stack of Higgs bundles, using code schemes. But I am really sure that if we take a stack, well, maybe a singular variety also, but a stack with some non-trivial automorphisms, if we take the cotangent bundle, then there is some derived structure. And if we just look at the H0, then we will find something like stable Higgs bundles. If we look a little bit around, and in this case it will be, we will take inverse image of other fibers. We will take other fibers than the 0 fiber for the moment map. then we construct some genuine algebraic varieties by taking stable points, and these also have a projection to the space itself, not the cotangent to that space.
What happens if you take lambda or t connection? That's a deformation of
yes, but I'm over finite field, so maybe. We'll see. Maybe you can recognize this thing will actually have a explicit description.
I mean, it could be that that's what you're constructing.
Maybe, I don't know. Okay, so because I'm going to use a local presentation, I have to explain a little bit all this local construction of Higgs. So let me start with so this is some kind of explicit construction of, let's start with a stack of vector bundles of rank R and degree D. And this is going to be via quad schemes. This is a standard construction, and here's a good reference for that. My favorite reference is a book by Le Potier called Moduli Space of Algebraic Vector Bundles on Curves, I think. Okay, so how does it go? I warn you, this is going to be not very canonical and so on, but let's still do it. So let us fix two line bundles. Usually you do this construction with one line bundle. I'm going to do it with two line bundles just for some technical reasons. So let us fix L1 and L2, two line bundles of degree n and m, and let's say minus n minus m, and we choose n and m very big. So the idea, we want to truncate this moduli stack of vector bundles, and the way to do it was we fix some line bundles, and we're just going to consider all the vector bundles which can be obtained, which are generated by these line bundles. Okay, so let me write a few notations. So just because I'm lazy, let me write alpha for the class RD, and then Li is going to be the value of the Euler form Li and alpha. And then I fix a vector space Vi, which is k to the power Li. Okay. And I want to consider, as I said, the set of all sheaves which are generated by L1 and L2. So I consider the following thing, which is called this quad scheme. This is the set of all maps from this Li tensor Vi, this particular vector bundle, to F. And I want F to be a coherent sheaf of class alpha. And here I take some kind of equivalence where really what I'm constructing is the set, when I'm considering the set of kernels. So I say phi is equivalent to phi prime if kernel of phi is equal to kernel of phi prime. So you can think of it as some kind of Grassmannian. And the basic theorem in this business is due to Grothendieck himself. It says that this space, this is, so you have to do it properly. You consider the functor from schemes to sets, which is defined using this, and you say this functor is represented by a projective algebraic variety. Okay, and there is an action, of course, of, let me write here, G is GL V1 cross GL V2 is a projective G algebraic variety. And the first approximation would be, well, of course, if you conjugate by G, you have the same class isomorphism class of sheaf. So I want to take the quotient by G, but the point is that there are maybe several ways that you can generate F by L1 and L2. And so you want to make sure that you choose only one. And so you have to choose the canonical. There is a canonical. If F is generated by L1 and L2, there is a canonical way to do it. So you just want to consider canonical surjections. So for that, you restrict yourself to an open subset. Let me write Q alpha. And this is the set of phi as before. To F such that, well, we want vector bundles. So that means F is a bundle of class alpha. And then each of these phi, they induce a map from VI to HOM LIF, just in an obvious matter. And so you want that phi maps VI isomorphically to HOM LIF, roll F. And this is open, and actually this is smooth, as opposed to this quad scheme, which is in general singular. Quad alpha L1 and L2. And now you can easily show that every vector bundle is represented by a unique G orbit, if you want. And therefore you can put, let's say, bun alpha. And let me still remember that there's a L1 and L2 here, is the quotient stack Q alpha over G. Okay. So alpha is in the same place. Okay, so this is an open substack, smooth, open substack. This is the way you can see that the stack of coherent sheaves of vector bundles is smooth, because this variety is smooth. So the open substack of bun alpha. And moreover, bun alpha is the union. So how to get all sheaves? You just need to send the degrees of these line bundles to minus infinity. Then you will generate everything in the end. And so it's just a union of these substacks. So these are smooth substacks which are of finite type. And so this also shows you that bun alpha is a smooth stack of locally of finite type. Okay, so this is our chart, if you want. It's not so bad. It's quite explicit. So now we want to take the cotangent to that stack. So we use this Hamiltonian reduction business. As was done in many talks this week. So let me do this explicitly in this case. What is T star of Q alpha? Where's the alpha? It's upstairs. Okay. T star of Q alpha, you can show that it parameterizes pairs phi theta, such that, well, phi is going to be a map, as before, from sum of Li tensor Vi to F. And this should be in quote alpha, in Q alpha. And theta is going to be a map from HOM, the kernel of phi, to F. And this is the cotangent stack. So it's you have to take the dual. And why is that? It's just because it's a tautology. It's exactly what I've been writing. The tangent space to phi of a quad scheme. This is exactly HOM from kernel of phi to F. If you think a little bit about it, it's exactly the usual formula for Grassmannian. So, okay. All right, and now we want to define the moment map. So the moment map fits in the fundamental exact sequence. fundamental exact sequence, which is the following. So there is a 0 here, which is not completely obvious, but you just apply hom towards f to the sequence defining phi, and you can take the dual, and you will get something like this. Hom kernel phi f dual. Then this goes to hom direct sum of Li tensor Vi to f dual, and then this goes to endomorphism of f dual. And here, this is via phi. This is canonically identified with the dual of the Lie algebra of the group. Okay, you think a little bit, and well, you have an identification between hom Vi f and you have an identification between, hom Lif and Vi. So that's it. And here is the moment map. This is your moment map. And so incidentally, from here, you see directly that if you take mu minus 1 of 0, what you get is this x1 f star. And we know that this is the tangent space to the stack of vector bundles. It parameterizes deformations of the vector bundle itself. This is self-extension. Okay. So what does Hamiltonian reduction tell us that we should do? We should take this mu minus 1 of 0 and then take the quotient by g. And what does the modern mathematician tell us to do? He says that you never take a fiber of a map. You just keep the map altogether so that you can also take non-zero fibers. And so let me still do the Dark Ages method. So mu minus 1 of 0 quotient by g. This is an open substack in Higgs bundles, a stack of Higgs bundles of rank r in degree d. And mu minus 1 of 0 is singular in general, so you see that this stack is singular, even though it's the cotangent stack to a nice smooth stack. And well, if you choose n and m big enough, so the degrees go to infinity, then you can consider the stable points, mu minus 1 of 0 stable, and then you take the quotient by g, then this is going to be isomorphic to now the moduli, not the moduli stack, but the moduli space of stable Higgs bundles. So this is the way you can realize this moduli space explicitly. You take n and m large enough, then you perform this Hamiltonian reduction, then you take the quotient. And here I just have to mention that the slope stability for the GIT, the slope stability that I define here is actually the same as the GIT stability from geometric invariant theory. You have to check that. It's not obvious. And so what is the idea now? This key idea stated in this very concrete language is you just consider other fibers of mu. Namely, you're going to choose a line L, so L isomorphic to A1 inside G star. And you're going to construct your deformation by setting Y is mu minus 1 of L stable quotient by G. This gives you, and here, actually, if I want to write this, which is what I will do, you have to take something in the invariance so that it's still G stable. And this explains to you why I chose 2 line bundles, so that this has a larger center. and if you choose the line generic enough, then this will do the trick for you. So this is the idea. Okay, so now let me make it a little bit more precise, generic, and the proof is simple, but maybe on the blackboard it will not seem so easy, but it's easy to check that if you choose generic enough line, then when you look at the possible values for the bundle F, it has to be indecomposable. So, and actually, yes, it's exactly the set of indecomposables. So, let me write some fact. This is easy. So remember that GCD of R and D was 1. So this means that we may choose L1 and L2 such that GCD of L1 and L2 is also 1. Okay, this will be necessary in order to have a generic element in the center of this Lie algebra. And then you set L is K lambda with lambda is, so lambda of U1, U2 is L2 trace of U1 minus L1 trace of U2. So essentially, if you identify G with its dual, it's just the L1 identity plus L2 identity. And then what do we have? We have that, first of all, lambda of identity is 0, and also lambda of E1, E2 is non-zero for any proper projectors E1 and E2. Okay, that's the genericity condition we need. And now you can see what's the relation to indecomposable. Is if you have an indecomposable vector bundle. If you have a decomposable vector bundle, then inside its endomorphism ring you have some projectors, and it won't be in the image of the moment map. Lambda won't be in the image of the moment map for this bundle. So let me just write this a little bit better. So lemma says that for phi in the direct sum of Li, for phi to F, now let, then L is inside the image of mu at the point phi if and only if F is indecomposable. This is the lemma you want. This is how you can relate Higgs bundles to indecomposable bundles. After you deform, you can choose a generic enough line so that this property holds, and just sketch of the proof. And really the proof itself is not much longer. Two things. If F is indecomposable, if and only if endomorphism of F is a local algebra, which means that any F in endomorphism of F, F is equal to C times identity plus some nilpotent part. Okay, and then the second point you need is that L is included in the image mu phi. From this exact sequence, it directly translates that so M it's in the image of this map if and only if it's in the kernel of the other map. And so if you can write it like this, lambda of F composed with phi is equal to 0 for any F in endomorphism of F. Okay. And so if F is indecomposable, then this fails, because of this property. Okay. So now we have all we need, and it's just a matter of studying this deformation and showing that it has the same number of points, and so on. So let me state the different steps and then give some ideas of their proofs. Okay, so now we put chi is mu minus 1 of L, and then chi t is mu minus 1 of t lambda is the fiber. And I have a projection from t star q alpha mod g to bun rd as before. And now the corollary of this lemma says that for t non-zero, the image of p t, what's the restriction, is equal to the indecomposables r d. And all fibers have cardinality q. You just have to compute 1 plus g minus 1 r squared. Okay, so this is what we want. And well, another thing that you can easily believe me is that if the line is generic enough, then all the points in this fiber are automatically stable. So when I do this GIT quotient, then y will only have something cut off at the 0 fiber. And so this property will still hold. So here's the lemma. For t non-zero, chi t is included in chi stable. And I say this follows from genericity of lambda. Okay, so let us sum up. To sum up, what do we have? We have constructed this family. Here we have y0, which is Higgs stable. And here we have, say, y prime. This is over a1 minus 0. This is over a1. This is 0. And everything is smooth. Everybody's smooth. All the fibers are smooth. Everybody is nice and friendly. And you want to check that, and one more thing, the cardinality, the number of FQ points of FQ, this is what we want. This number of indecomposables. So what we're left to show now, it's enough to show that the number of points in y0 is the same as the number of points in any yt. Okay, and you can immediately notice that all the fibers yt are the same for different t's. Right? So it's you have a degeneration at 0, but otherwise they're all the same. And so actually it's also enough to show that q times the cardinality of y0 of fq is equal to the cardinality of y of fq. Okay, so this is the final thing you need to prove. And so this is maybe the most interesting part. So how do we do this? Well, the natural idea is to use this GM action, which is rescaling of the Higgs field. So exactly the GM action that acts with weight 1 on A1, just multiply theta by Z. You want to use this to get a decomposition, a Bialy-Nicky-Birula decomposition of your whole space. And of course, everything will be, the fixed point will be concentrated in the central fiber. And because of this Bialy-Nicky-Birula decomposition, we can either compute the number of points in the central fiber in terms of the number of points of the fixed points, number of fixed points, or we can do the same for the whole variety. Okay, so this is the proof in a nutshell, but there's just one point you need to check. So let me just say there exists a GM action on Y, simply phi theta, well, Z times phi theta is phi Z theta. And so the key point is that this action is contracting. Which means that every point in Y has a limit when Z, so Z applied to that point converges to something in Y. It does not go to infinity. And this is not obvious because Y is not projective. Okay, moduli space of Higgs bundles, stable Higgs bundles are not projective. So admitting this, then you can write, or you can look at the fixed point. This is a union of Zi are smooth and they're projective varieties. And the Zi belong to Y0, actually. And then you have a Bialy-Nicky-Birula decomposition of two things. First of all, Y is going to be union of, let's call them Zi plus, and each Zi plus is an affine vibration over Zi. And you have the same thing for Y0. Zi0 plus, and each Zi0 plus, let's say dimension affine vibration, dimension is equal to di, and here we have affine vibration, and dimension is equal to di0 Zi. And how do you compute di? Well, you consider the tangent space at a point, and you look at the number of eigenvalues for the action of Gm, which are positive. And in any case, the tangent space to Zi in Y or in Y0, the only difference is a one-dimensional thing. It's the base. And Gm acts with positive weight on the base. So from these, you can get that di is equal to di0 plus 1. And then you're done. Okay, so this is a classical argument. But what you need to show this, for this to work is that this action is contracting. So this is what you're left with. And let me just mention briefly how you do it. Well, let me just say a few words, not much at all. So, proof of key point. Well, if you restrict to Y0, which is a moduli space of Higgs bundles, this is very classical. It's because you have this Hitchin map. It's a different mu. We call it mu. This is a Hitchin map. And it's proper. It's proper, and GM equivariant. and the GM action on the base is contracting. So if you have a situation like this, then morally your point here will map to something which will contract to 0, and it's stuck in the fibers, which are projective, so it has to converge, and so then the map is contracted. So for y, you need to construct let's say an avatar of the Hitchin vibration. And my construction is a bit ugly. It's not very canonical, but nothing in this business is really canonical. But I will just say that for this, I use some results of Alvarez Consul, some constructions of Alvarez Consul and King, and Alistair King. Okay, so this concludes the proof that, a sketch of the proof that number of stable Higgs bundles is related to the number of indecomposable vector bundles. Okay. So I promised that I would give another proof. How much time do I have? Okay. So I promised I would give another proof, and I won't. I will just write a few words. So this is you could say geometric proof of this, direct geometric proof of the equivalence between counting indecomposable and counting stable Higgs bundles. But there's a second method, which is purely algebraic, let's say, which hides all the geometry. This is joint work with Sergei Mozgovoi. And let's just say that this is more, you use whole algebra technique, whole algebra techniques, and this Eisenstein series business. So you have Hardan-Arasima infiltration. You have this truncation. So the proof goes a little bit like the proof for computing the number of indecomposable. You have this Jordan decomposition. But the point is that we use this for the category of Higgs bundles. And we can also do it in the case of twisted Higgs bundles, at least when the degree is larger or equal to the degree of the canonical bundle. And this category is of global dimension 2. So a priori, you cannot use this Hardan-Arasima infiltration type business for categories of global dimension 2. But here, luckily, we use some nice cohomology, let's say x2 vanishing in some cases that still allow us to use whole algebra techniques. So we get the same result. We get a stronger result in the sense that we can compute twisted Higgs bundles also. And it's also pleasant that we can get rid of this dark ages business and do something which looks modern.
Can you say the word why in principle you can't use Hardan-Arasima infiltration?
Because, so what you want to compute, essentially the Hardan-Arasima infiltration is something like this. You want to compute one, say Higgs, RD, against a product. One Higgs stable alpha 1, one Higgs stable alpha R. This is the kind of things you need to compute, right? And you say that this is going to look like this. Okay, this is the usual thing. And then you say, okay, to compute this, I just use the fact that the Hopf pairing is dual. And here you have, the product. but then this you cannot compute this. So this is nice only in the hereditary case. So another way of saying it is that you have this integration map, this Reinecke integration map. It's a morphism of algebras to this quantum torus. It's a morphism of algebras only in global dimension 1. Or it's a morphism of algebra when you have x2 vanishing between these elements. So you need to check that you have this x2 vanishing in this case, and therefore you can still apply these techniques. Okay. So this is the statement. This is the proof. Now I need to give you the statement. So I cheated a little bit. So this is the formula. This is the formula, the explicit formula for this AGRD. So it's complicated. I still want to comment a little bit. So you define it using generating functions. This is a rather standard trick in this whole algebra business. So it's like summing it for GLR for all R's. And so you introduce a certain rational function, and this rational function appears as the log, a big plastistic log, of something interesting. So this something interesting is parameterized by partitions. Partitions is Jordan types, nilpotent orbits, if you want. Then you have a nice friendly term. Now you have two terms. So this J lambda, so this is a definition of the plastistic log. It's some combinatoric stuff. J lambda, this is a product of zeta functions. And you take the product of zeta function for all boxes in this partition, and then you evaluate at points, at powers of q and this variable z, twisted by the leg length and arm length. This is some very classical combinatoric stuff that you get in the whole algebra, in the Hilbert scheme or instanton business. Okay, so this is, I would say this is related to L functions. So the zeta function is kind of the L function. It appears when you compute the volume of the moduli stack of G bundles. Okay. And then you have this other term, this H lambda term. So this term looks a little bit strange. I think it's kind of a new type of expressions. But still, it has some it has some terms which have been seen before, especially this term. This is a product of zeta functions, and you evaluate it at zi over zj for I different from j. This is something like you evaluate it at all positive roots of your root system, this zeta function. And then you take a sum over the symmetric group, of the Weyl group. You have this term, so what you really get is the ratio of this divided by this. This kind of term often appears when you compute the constant term of Eisenstein series. This is how they will come up. And then you have this extra term. So here you can recognize something is related to the structure of the root system. Here it's obviously the simple roots, and here it's obviously the center of GLR. Okay, so I would say this looks like it could be generalized to other root systems, but the method that I've been using to compute number of stable Higgs bundles doesn't, because I really used the coherent sheaves at some point, and so this is not available and only replaced at a high cost for G bundles. Okay, and then once you define this rational function, then this AGRD is given by a certain sum of residues. So this big rational function, it's not obvious at all, but this big rational function only has simple poles, and this simple poles at most at rth root of unity. And the conjecture is that it only has a unique simple pole at z equals 1, and that the number of indecomposables which you want to compute is exactly the residue at this point, up to a sign. And this is, in particular, if this conjecture holds, then AGRD does not depend on D. So this is exactly the statement that AGRD is independent of D. And this is expected, and it's reduced to some very complicated combinatorial problem, which is probably very difficult to even check in cases. But okay, so now I want to finish just by making some comments. So I first have to talk about the work of Hausel and Rodriguez-Villegas and others. So I think this is just a blah, blah, blah. So maybe first of all, just a quick comment. You can compute the number of points of the, how do you say? Let's write it like this. Nilpotent cone, stable nilpotent cone over FQ, essentially using the same kind of Bieliniki-Birula business. You can easily deduce it from the number of points of the total moduli space of Higgs bundles from stable Higgs bundles. And so in particular, you can also compute the number of irreducible components in this stable Higgs bundles. And this number of irreducible components should be very interesting. There are some conjectures by Tamás Hausel and Rodriguez-Villegas on this number, and also it should have some nice representation theoretic interpretation. I hope I have some time to talk about it, but okay, so I just want to say we can do that. Then, because this moduli space of stable Higgs bundles is known to be pure, and we have shown that it is of polynomial count, because all these functions are, because this number of indecomposable is a polynomial in the Weil numbers of the curve, then from this you can deduce that you can compute also the cohomology of the moduli space of stable Higgs bundles for x over C, and you can also do it for x over FQ. And you take the étale cohomology, and it also implies that for x over FQ, you take the étale cohomology, all the Frobenius eigenvalues are monomials in the Weil numbers. So it's something like a very pure algebraic variety. Okay, and because you have a diffeomorphism, at least when x is over C, you can also compute the cohomology of the so-called character variety, or twisted character variety. This is the twisted character variety, so representation. So representations of pi 1 of your curve of genus G, isomorphism class of representation, twisted representations, not the stack. It's also very interesting to compute the cohomology of the stack, but here just it's kind of a stable part. Okay. And so I will come to that just in just a minute, but let me mention a few people who worked on this cohomology of stable Higgs bundles. So computing the cohomology of this moduli space of stable Higgs bundles. So this was done for R equals 2 by Hitchin in his, maybe not in his original paper, but in the paper very close to it. And then R equals 3 was done a few years later by Gotten. I think he was a student of Hitchin. And then I would say breakthrough comes in 2006 with the work of Hausel and Rodriguez-Villegas. And so they not only came up with a conjecture for the cohomology of the moduli space of stable Higgs bundles, or character variety, but actually they have a conjecture for the mixed Hodge polynomial of this twisted character variety. And this mixed Hodge polynomial, you can specialize it to get the Poincaré polynomial. And so in particular, although the specialization is not easy, in particular, they have a very nice conjecture. In particular, this implies a conjecture for the cohomology of this thing, and therefore for the cohomology of this moduli space of Higgs bundles. So, so their formula is quite similar to that one. So it's also very complicated if you want. It's a bit less complicated in that it doesn't contain this H lambda term. So it's my favorite term, but it's not in there. And so in particular, I don't think it will be very easy to deduce their conjecture from this computation, even for the Poincaré polynomial. But it brings us to one nice point, is that these cohomologies are the same because of the diffeomorphism, but this is an analytic diffeomorphism. And here we have this mixed Hodge polynomial, so we have filtration, which is given by the Hodge filtration, by the weight. And here there's also a filtration coming from this so-called perverse filtration coming from this map to the moduli, to the base of the Hitchin fibration. And so we have three types of filtrations. Actually, we have here M twisted GR and the weight filtration. And then there is cohomology of Higgs, stable RD, with the perverse filtration. And these are conjectured to coincide. This is a conjecture that lots of people are thinking about. It's very puzzling. It was proved in some cases by Hausel and De Cataldo and Migliorini. And now there's a third one, which is maybe less nice because it's not a filtration on spaces. Rather, it's a filtration on dimensions, if you want. You have this number of indecomposables, absolutely indecomposable, say A, G, R, D, plus the Harnar-Narasimhan filtration, which means that you can look at the number of indecomposables within given Harnar-Narasimhan strata, or at least whose minimal slope is bigger than something. And in the proof of the count of this is what you count actually. So it's also a polynomial, and you also have a formula for that. So it seems natural that you want to relate this filtration to this weight or perverse filtration. And Emmanuel Letellier has done some computations on parabolic P1 case. And in some cases, there's some coincidence. Okay, so how much time do I have? Or don't I have? I have 1 minute. So I just want to finish with some analogy with Katz's theorem and something maybe a bit relevant to this geometric representation theory meeting. So some representation theory. So let me try to be quick. So this is an analogy with Katz's conjectures, conjecture for Quivers. Since just writing this now I only have 25 seconds, let me not mention, there's one conjecture which says that AD of Z, it has positive coefficients. Okay, this conjecture is more or less here in the case where R and D are relatively prime because of this formula. No, not because of this formula, because it computes the number of points of a pure variety. So you can identify it with the cohomology. But the one which I am more interested in is the fact that the constant term is equal to the dimension of a corresponding weight space in the Kac-Moody algebra associated to your quiver. And so there is no good analogy for G, at least that I know, for GQ for curves. But there is a good analogy for UQ plus GQ, namely this spherical hole algebra. So you really want to expect that this AD0, which, well, on the one hand, is related to the number of irreducible components in this nilpotent cone, stable nilpotent cone, you really expect it to be related to the dimension of U of the whole algebra. Sorry, not the dimension, number of generators. Number of generators for this spherical whole algebra. And this type of things is typically at the center of this Donaldson-Thomas theory. And so this suggests that one should study Donaldson-Thomas invariants for two things, the G-loop quiver and also actually the moduli stack of Higgs bundles. And somehow the DT invariance that you should get from here should be related to the number of generators for this spherical hole algebra, and therefore also number of irreducible components, indecomposables. And one final word, when G is equal to 0 or 1, you can make this very precise, and you can check that it's true. But, okay, that's all. Sorry.